Hello interwebs, welcome to Board Repair Basics. In this video I'm going to tell you the right way to do voltage injection, how to do it, when to do it, but more importantly when not to do it. Because it's a very misunderstood technique that a lot of people see as a magic bullet, but actually should only be used at the end of your diagnostics. So let's roll the intro and get into it. So this video is going to be broken up into two halves. The first half I'm going to tell you all about voltage injection and all of the stuff that you should know but most videos don't tell you. And the second half we're actually going to do voltage injection on a laptop and actually fix it. So first of all, the big thing that people need to know. There is a very common misconception that voltage injection is just this magic bullet technique that fixes any broken motherboard. And this kind of isn't surprising because I've done countless videos demonstrating voltage injection, as have other people, and it makes us look like heroes when suddenly the dead board isn't dead anymore and we just magically know where the fault is. So I'm not surprised that a lot of people just believe that it's this one fix all technique. But we're actually doing it because we've already jumped ahead in the diagnostic process without actually saying all of that bit that we just skipped over. And I know that this is a problem because I routinely see people in comments sections on other videos and often in my own videos when I come up, if it's a video where I've come up against a brick wall, there'll be someone in the comments going, oh, just inject voltage and that'll tell you what the broken bit is. And based on that video, I'll read that comment, look at it and be like, no, that's not how that works. That's not going to solve anything. And it tells me that this person does not understand what voltage injection is actually doing. So it proves that this issue is real. So before I lead you on this long rabbit hole of discussions and do's and don'ts, I suppose I should answer the obvious question, what is it for then? Well, the short answer is that voltage injection is a method to find what component is failed when you have an entire rail that is shorted to ground. So if we have a power rail, say for example the main power rail in the laptop that is reading 0 ohms to ground, we'll talk more about that in a moment, we have no idea what part of this rail has actually failed and is pulling it down. There are a lot of components on some of these power rails, and through trial and error you will never find the answer, especially if there's no visible damage on the board. And the rail won't power up because its own power supply is detecting a short circuit and refusing to switch on. So voltage injection is a method where we connect up an external power supply and push power into the rail. This power will go through whatever component is shorted and cause it to heat up, which reveals the faulty component to us. So firstly, we need to define what a short is, because this is also another misconception. And this is a misconception because the term short gets thrown around quite a lot and is often not clearly defined by the people who use it, again, including myself. So there are two types of common shorts that you're going to see. There is a component that is shorted through, meaning that a component that should be doing some kind of function or offering some kind of resistance has internally fused and effectively become a wire. And then there is a short to ground, where a component has once again fused or malfunctioned somehow and is bridging one side of it directly to ground. Now, although the mechanics of how this work are the same, the effect is very different. For example, if you have a component that is bridging a whole rail down to ground, then you have a short to ground. And a power rail that should have resistance on it is now going to show very low or 0 resistance to ground, and thus cannot power up. However, if you have a component that is shorted through, then the power rail may be directly connected to another power section that it should not have a direct connection to, but this doesn't necessarily take it directly to ground. That part is critical because if you have a short through to another section, that is not a time when you should be injecting power. I will show you an example of what this means later on. I'll show you an example of something where we have a short through and a short to ground. So in addition to this, we also have to decide, what kind of things can be shorted through or to ground. Commonly, we are showing this on power rails. That is the most common time where you will find this. A signal trace can be shorted to ground or have a short through somewhere. However, signal traces, you should never be doing injection on a signal trace unless you already know what you're doing. And that's something that's going to come in with more experience. If you're learning how to do voltage injection from this video, you should not be injecting on signal traces. And the reason for this is that they are connecting to important things and may have little to no protection against someone jamming 5 volts and 3 amps into them. That's how you end up with a dead PCH. And finally, also, before we move on to the next section, we also need to talk about how we are measuring a short to ground. So a short to ground we are going to define as being less than 1 ohm of resistance to ground. So by that I mean I take a multimeter and I measure from the power rail that I believe is faulty to a ground point. And when I'm measuring, I should be measuring in resistance mode, where it shows me the number of ohms between the power rail and ground. And that number of ohms needs to be less than 1 before we define that as a short to ground. Do not use beep mode or continuity mode. If I put my multimeter into continuity mode, it beeps. And when I touch the probes together, it beeps. So because there is continuity between the probes. So this is often used as a quick and dirty way to find shorts to ground. You just put your black probe on ground point and then you touch around with the red until you hear a beep, right? And this can be useful when you're doing very broad checks, when you're literally just sanity checking, looking for something that is vaguely not right. However, most multimeters in continuity mode will beep at, it could be anything below 40 ohms. A lot of them might be significantly lower. They might be set to like 20 ohms, 15 ohms, something like that. But remember, our short to ground needs to be less than 1. And basically any meter is going to be beeping way before you get that low. So continuity mode or beep mode is functionally useless for checking if you have a short to ground. You can use it when you're doing your initial checks, but a beep does not mean a short. Again, I'm being thorough with this because of the number of people who get it wrong. I myself got it wrong in many of my earlier videos where I've been probing around, I've heard a beep and been like, oh, I'm shorted, when actually I wasn't at all. Those videos are wrong and I'm sad about it. So next we need to talk about low resistance circuits, and this is very important and ties into our talk on continuity mode just then, because there are circuits in a laptop or a desktop computer which are normally low resistance and are very commonly misidentified as being shorted or faulty. So classic examples for this are vcore rails. So for example, CPU vcore, GPU vcore, or the PCH core power rail. These chips, CPU, GPU, PCH, they naturally have a very low resistance going through them down to ground. So the power rails to them will naturally read low resistance. So I generally refer to this as low resistance through silicon. This isn't a technical term, it's just how I call it. So when you hear me say with going through silicon, I'm talking about CPU, GPU, or PCH, or a big silicon chip like that naturally has low resistance. For example, CPUs will often read like 3 or 4 ohms. GPUs can be even lower, they're often like 1 or 2 ohms. And the PCH, again, will also be low resistance. So if you hit these while you're beeping around in continuity mode, you can very easily think that your CPU is shorted to ground. But in reality, that's what it normally looks like. If you check in resistance mode, there will actually be a couple of ohms resistance, and that is completely normal. Now, this isn't to say that you can't have a fault on those rails. That may actually be where your problem lies. And what we need to do is we'll need to check if those are causing a problem. And I will show an example of this later on in the video. So again, stick around, but again, understand that low resistance is a thing that exists. So next, let's talk about equipment that we're going to use for voltage injection. So we're going to need, obviously, your multimeter and some nice probes for actually measuring circuits. You're going to want a DC bench power supply. So the one that I use is this Hanmatech HM305P. This particular one comes in various flavors and brands, but the important thing is that it's a variable voltage, variable current power supply that has control current and control voltage mode. And this is important because when we apply power to a shorted rail, we are effectively putting our power supply into a dead short circuit. This means we have to control the amount of power that it can deliver, because in a short circuit scenario, your power supply will dump everything it has into that circuit. And this is the reason why, no, you cannot use your mobile phone charger and you cannot just hook a LiPo up to it. Because when you hook up an unconstrained power supply like this, it will dump everything it has into that. Now, you might say, well, fine, that's going to dump it into the faulty component, right? That's no problem. Yeah, but if you blow open that short circuit, for example, if you have a shorted capacitor and you explode it with 5 amps of current, what's next in the chain? It could be something that wasn't damaged and now gets disintegrated by your LiPo battery. So when you're going to do this, you do need to be using a proper DC bench power supply. There are some specialist tools out there for this. You can get special voltage injection boxes that do this. However, in my opinion, I don't think they're particularly useful because a DC bench power supply can do all of that and lots of other things. So it offers significantly more utility than just injection. Then the other bit of equipment that we're going to need as well is while we're injecting, we're going to be creating a heat source with that injection, and we need a way of finding that heat source. So this could be using just your fingertips. You could be touching the board and looking for a hot spot, which is how I used to do it. You could use freeze spray, so a little can of refrigerant or an inverted air duster that freezes the top of the board and makes a frosty area, and you'll then have a melting point where the heat is. You could use the rosin flux technique, where you burn some rosin flux and you waft the fumes across the board, leaving a deposit that will evaporate where heat is. You can also use alcohol that also evaporates very quickly in heat to identify a spot, or you can do it the easy way and use a thermal camera. Thermal cameras are not especially cheap, however, they are hugely more affordable than they used to be. And as someone who has used multiple other methods and these days uses a thermal cam, just buy a thermal camera. They're so much better than all the other methods that once you have a thermal camera, you will wonder why you ever bothered using any of the other exotic methods for doing this. Just buy one. So now we've put down a lot of definitions and we've talked about the equipment that we need to use. So how are we going to set up that equipment? So obviously most of the setup is down to the power supply. The long and the short of it is that we're going to inject at 1 volts. And if you're using a thermal camera, you can probably start at 2 amps. However, I usually inject at 3 amps. That's usually what works for me. Now, if you are working on a GPU, the setup will be different. However, GPUs are outside the scope of this video, so I'm not going to talk about that, but just keep in mind GPUs, you want to be lower, like 0.8 volts kind of thing. But we won't go too far into that from here. And now I also need to talk about Ohm's law and what potential difference actually is. Because a real classic hang-up when people first start doing injection, which was certainly the case for me, is when you connect your power supply up in a dead short circuit, what you're basically doing is this. It's just that, but you've got a short circuit through a motherboard in the middle. Now, remember, voltage is potential difference. It is a potential difference between the two probes. Now, if you connect them up to each other, there's no longer a potential difference there because they're directly connected. So what's going to happen is while you're injecting, your voltage is going to drop. And this will be a function of Ohm's law. your voltage will drop based on how much resistance the short to ground actually has. And this is why you need to be below 1 ohms in order for a voltage injection to work. Because if you have more than an ohm, maybe more than 1.5 ohms of resistance, you're going to need an awful lot more voltage to push current through that resistance. And this means that you're using a lot of power. And if you need that much power, you are probably not shorted at all. So again, this is one of the reasons why I see lots of people saying to do injection when the circuit in question has got 20 ohms on it. And it's like, you can't inject on that kind of resistance. You'll need all of the power your power supply has got to force power through that. And if you have that much resistance, there's no short circuit to begin with, which means you have a completely different fault, which means you shouldn't be injecting voltage in the first. So the short answer is 1 volt, 2 or 3 amps. You can push up to 4 if you're desperate. However, that's going to be because you have run into some kind of extraneous circumstance. Cool, so I'm done waffling. Let's get to a demo board and I'm going to demonstrate how to find a fault that requires voltage injection to resolve. So the example laptop I've got in front of me is an Acer Nitro, and it has a shorted main power rail on its motherboard. So we can quickly check this by having a look at the input capacitors to the CPU VRMs that are down here. I'll just quickly show you what that looks like. I'll turn my multimeter to resistance mode. And if I put my black probe on a screw hole for ground, and we go up onto one of those capacitors on the positive side, you can see there that we're sitting at 0.2, 0.3 ohms, basically 0, well below an ohm. So this is to all intent and purpose a dead short to ground. So this is what we want to see. This is a perfect candidate for voltage injection. So what we're going to do is we're going to take the motherboard out of the laptop, and then we can take a closer look at it and check that we are cleared to do injection. So let's disassemble this thing. So we've got our motherboard out of the laptop now, and we know that we've got a short circuit down here. However, again, it's very important when you're doing voltage injection to understand what you're doing. So by this, I mean we need to look at the short circuit we found. We need to know what that rail is doing and why it should not be low resistance. So in this instance, the point that I measured was the input capacitors to the CPU VRMs. These guys are always going to be on the main power rail because they're one of the most power hungry components in the laptop. So they're going to sit on the main power rail, and this is a classic place to find a short circuit. The main power rail is one of the biggest current handlers on the board, so it's the most likely place to have power failures. It's not the only place where you can have failures, but it is a very, very common example. So we know that this is the main power rail because it's feeding into our MOSFETs, and we know that the main power rail should not be low resistance. So we know that this is short-circuited and it is not supposed to be short-circuited. If you're measuring somewhere else on the board, and again, I've seen examples from people where they've measured random spots on the board and they've gone, oh, this is measuring zero ohms to ground. It's like, okay, but what is that? What have you measured? If you can't answer that question, then you should not be injecting power. If you've just found a capacitor on the board somewhere that's reading 0 ohms to ground on both sides, you need to ask yourself, well, what is that capacitor doing and why shouldn't it be shorted? You're going to need to find out by looking at schematics first. So make sure you understand what it is you've measured. For this one, we've got a nice easy example of the main power rail, but again, it is really important that you check what you're measuring first. Don't just stab in and go, that's a capacitor with 0 on both sides, therefore it's a shorted rail. Okay, but what is it and why shouldn't it be shorted? Because there are plenty of signals that are just normally low resistance. So again, keep this in mind. So because we've got a short on our main power rail, and it is also powering the VRMs, we need to be very careful here, because if we have a MOSFET that is shorted through, then we have a direct path from our main power rail into the CPU. We can't inject on that, because if we plumb any power into the main power rail and there is a shorted MOSFET, anything we inject here goes straight into the CPU. And that's bad. Same thing goes for the GPU over here. If we had a shorted MOSFET, like we've got some power stages up here, if one of these guys has gone short circuit and is plumbing power directly through to the GPU, then anything we inject is going straight into silicon. And that's how you blow up something that might be savable. So how do we know if we have a shorted MOSFET? Well, there are some easy giveaways we can do. So let's drop back into resistance mode on our multimeter. And once again, we're going to pick up our shorted power rail. So I'm going to go over here and I'm going to measure where I last saw the short circuit, which was here. And once again, we're seeing that 0.3 ohms. Now that 0.3 or so we've got, that's probably in my probes and the probe leads. So you're never going to get truly down to 0. So keep that in mind. So that's fine. Now, a very quick way we can tell if we might be shorted through silicon is just to measure the other side of the MOSFETs. These MOSFETs create a barrier between the main power rail and the CPU's power supply. They are supposed to be stepping the voltage down going through there. So if we check the other side of them, if we check one of these inductors, we should see a different value. And we do. We've got 3.3 ohms or 3.2 ohms. And that is completely natural to see that amount of resistance going through the CPU. And this is where another misconception comes in. A lot of people will measure these guys in continuity mode, in beep mode, and your multimeter will beep. If I go into beep mode here, we go, oh, it's beeping. Oh, my CPU is dead. No, your CPU is fine. It is low resistance. This is completely normal. So we've got 3 ohms there, but we have 0 ohms over here. This is good because it means that all of these VRM MOSFETs are completely fine. Now, we're also going to check the other inductors here. We've got a row of 4 that creates CPU vcore. We've got this guy over here that is probably our system agent. Let's see what he's doing. That's 7 ohms. Again, it's low resistance, but it's not 0. It's not the 0 ohms we're seeing on our shorted rail. And over here, probably the iGPU or something, 20 ohms, no problem. That's absolutely fine. So let's do the same treatment up here at our GPU power. So once again, I'm going to go onto a screw hole and I'm just going to check the inductor. And we've got 1.7 ohms. So again, we're even lower than the CPU at 1.7 ohms, which is really low. A lot of people will take one look at that and go, oh, that's short. Nope, that's completely normal for silicon. However, again, that is not the 0 ohms we're seeing at the main power rail. We can go to our input capacitors up here, and we're going to see 0.3, which is our real short circuit. There it is, 0.3. And if I go to the other side of those capacitors, which is actually ground, we should manage to get a little bit lower still. 0.1, that's actually ground. So you get the idea. So from here, we've now established, and you know what? We've got another big inductor over here. I'm going to check this guy as well for good measure. It doesn't hurt just to check any big power supplies you've got on the system, or even all of them, and see what their resistance is to see if any of them match the short circuit you're seeing. This guy's up in the hundreds of ohms, no problem at all. Now in this bit of footage, I'm measuring the VRMs on a very similar board to this one. I think it's actually identical. And what we're seeing here is a few ohms on the main power rail. This means we have a shorted MOSFET going into the CPU. Now, at this point, we can't inject because any injection is just going to go straight through this MOSFET and straight into the CPU. Now, just because you have a shorted MOSFET, it doesn't mean the system is dead, although you're in a lot of trouble if you're in this situation. However, diagnosing a shorted VRM is outside of the scope of this video, so I'm going to gloss over this bit. However, again, if you see a couple of ohms on your main power rail, you're not in a dead short. You have a short through a MOSFET. And that is a different kettle of fish to what we're seeing on our example now. So we've established that we have a short circuit where there should not be a short circuit. We have established that we are not shorted through a MOSFET into silicon, and we're ready to start setting up for injection. So I'm going to remove any other small objects from the board just to make sure there's no complications here. I'll take the memory modules out, and I'll remove the wireless card over here for good measure as well. We want to make sure the board is nice and clear so there's nothing hidden under another device that we might not have spotted that might be in our way. And I've made some room on my desk just to make sure that I can move the board around freely and look for things without elbowing things off the bench. And so now what I'm going to do is I'm going to solder some jumper wires onto this that I'm going to use to inject power. Now, as for where to solder our jumper wires to, well, we want to put a ground wire on, and the ground wire can go onto any ground. So in this case, I'm just going to solder on directly onto a screw hole. Because the screw hole is a nice big solid ground and it's easy enough to tidy up afterwards. We can put a nice big blob of solder there and clean it off when we're done. My positive jumper wire, I'm going to put onto anywhere which is shorted, basically. And in this instance, I've got a nice empty pad where there would be an extra capacitor here. So I can solder onto that positive pad there, and that will work nicely. We can also solder onto other places where the main power rail will pop up. So we could trace that back through the system. If we go over to this area of the board, this is where the battery connector is and the DC in connector is. This is a place where you're going to find the main power rail. In this case, on the back of the board, we've got DC in MOSFETs and then a current sense resistor. This will almost certainly be shorted to ground as well. So you can measure here to check. And you know what? Let's do that because it costs nothing to take more measurements. So I'll put my black probe on ground. Let's just check the back of that current sense resistor. And that guy is also shorted. There we go. And if you want to learn more about tracing the main power rail around the laptop, then by all means, check some of my other videos where I've done voltage injection, and you can see me going through this. However, we don't have time to do that in this video, but this is something that you should understand how to do. You should know how to trace power through a motherboard before you start doing this kind of thing. Again, don't blindly inject. That's how you blow stuff up. You need to understand how power moves through the board before you can start doing injection. Okay, I'm going to prepare these surfaces with a bit of fresh solder. There and there. And solder some jumper wires on. So it doesn't matter what color the jumper wires are, just remember which one is which. However, you do want to make sure that you're using nice thick wire, because if you use thin wire, you're going to be pushing a few amps down this, and you don't want the wire to be heating up instead of your short circuit. There we go. So we've got that in. I've made sure it's not going to touch any other pads that it's not supposed to. And that's a nice confident connection. And now just to make sure that we're not going completely insane, we'll just measure the resistance between our two injection jumper leads, and we should find that we have 0 resistance. And there's our 0.3 ohms again, which is all in the wires. So we're all set to go. So let's get our power supply set up. So I've got my power supply set up at 1 volt and 3 amps. Now, because I'm going to be using a thermal camera, I probably don't need 3 amps. So let's just scooch that down a little bit. I'm just going to tone that down to 2 amps. And we can always turn the power up a little bit if we need to. Now, before I connect it up, I'm just going to demonstrate, again, what to expect to see when we switch it on. So if I turn on the output, you can see that we've got our 1 volt set, and we're currently passing no amps, because we are not connected together. Now, if I connect the crocodile clips together, you can see that our voltage has dropped down. We've gone down to 0.1 volts and we've gone up to 2 amps. This is because the potential difference between our connectors is 0 because they're directly connected. They're shorted together. So our voltage has dropped down. Even though we've set 1 volt, we're only getting 90 milliamps here. However, we're passing 2 amps of current through this short circuit. So this is really important to know, because when you first start doing voltage injection, you'll connect it up and you'll be like, well, the voltage is 0. So you'll try to turn up your voltage, but nothing is happening because you're in a short. So again, really important to keep this in mind. So let's turn off our output again. And I'm now going to connect the crocodile clips to my jumper wires. Make sure you've got a nice good connection here, because a poor connection will ruin your day. Right, now let's switch to a thermal camera view, and we should see something happen when we turn on the output. Right, so we're all set up on thermal camera vision now. My thermal camera doesn't auto-calibrate. My thermal camera doesn't have manual calibration, so I'm going to keep my hand just slightly off shot here, just to keep the board the equivalent of cold, which is what it is. Because if I move my hand off shot, it tries to average everything out. So keep that in mind as we watch it. So let's turn on the output from the power supply, and hopefully we should see something flare up. So as you can see, our power supply has dropped down to 270 millivolts, and we're passing 2 amps. So something on the board now is absorbing that 2 amps and getting warm. So I'm just going to move the board about, keeping one hand in shot, and we're looking for something that is heating up. So beware of reflections, like that little hot spot there, that's just a reflection. There's nothing screamingly obvious. Okay, let's turn the board over. And this is why I like to be on jumper leads, because I can now just lift and turn the board. Nothing jumping out on this side either. Alright, so we might need to go to 3 amps here, because whatever it is quite happily tanking that current without spitting out a lot of heat. And you'll notice that the voltage has pushed up a little bit. That's because there is some resistance in this board. So that means as we force more current through it, we need more voltage to push that current into the short. Let's bring it up a little bit closer and see if we get any more detail. So you can see we've got reflections moving there. But there is a little spot there that's consistent. Might be this tiny little chap there. That might be our guy. Okay, so I believe I've found it, and I think it's this guy here. You can just see my screwdriver pointing in there. I think it's that capacitor there. But this one's really tough to find because it's around a very high power area that's capable of sinking a lot of heat into the board. We're going to need to go under the microscope to take a proper look there. So let's switch off of the thermal cam and go under a microscope and see if we can confirm that. Not the black and white answer I wanted for a demo video, but definitely enough to show you that sometimes it can be really difficult to spot these. It's not always a big crystal clear flare up on the board. Right, and under the microscope we can see that this guy looks pretty unhappy. If we come in from the side there, you can see that looks like a big old crack in the side of it. So I'm pretty certain that we've got our answer there. Let's put a little bit of alcohol on that, see if we can confirm. However, I don't think we're going to see a big effect from this because the spot that we're sitting on is right on top of GPU vcore. So we've got these huge power stages nearby going into massive inductors and another secondary power supply right there. This is all sitting on top of 2 big power planes. And those power planes are like anchors and they just suck up the heat. So I'll turn on the power supply again, and we'll just put just a little bit of alcohol on there and just see if we can spot anything. So I'll just use my finger just to dab the alcohol on top of that. There you go. So you can see that that guy is drying out almost immediately. The chip next door to it, that is wet. That's got alcohol sitting on top of it. And all of these resistors and stuff, they're just sitting wet under the alcohol. But that capacitor, that dries out immediately when I pull some alcohol across it. So that's how we know that that's our culprit. You can see how the effect is quite subtle. In extreme cases, you can get the alcohol to bubble around it and stuff like that, and you'll literally just see it boiling away. But when you're on power planes like this, the effect can be very slight. And this is why alcohol is not a sure thing. So we needed a combination in this case. The thermal camera helped us narrow down roughly where it was, and then the alcohol helped us confirm it. So what we're going to do now is we're going to take this guy off the board and see if that solves our problem. Now, because this guy is sitting on a big power plane, it's going to be a bit rough trying to get the hot air in there. So I'm going to use some low melt solder, and I'm going to see if I can soldering iron this guy off. We'll find out. Even if the soldering iron can't get it off, the low melt solder will make it a bit easier for the hot air station. So we'll just get some of that on each side. Now I'm just going to try and heat both sides of this at the same time and tweezer it off the board. Oop. There we go. And I made a little bit of a mess there, so we'll just tidy up those pads. Put a little bit of flux. That's a jumper spot that we just messed up, so we'll just reflow that. It's funny, the one time you want a big old solder blob, and it won't go. So now we've removed our suspect capacitor. Let's go back into resistance mode on the multimeter and we'll check if our short circuit is gone. So we'll just check across the point where we were injecting, and our main power rail is no longer shorted to ground. We now have tens of kilo ohms and rising, 60,000 ohms. Excellent. So we've now successfully identified the fault. We have removed a shorted capacitor from the motherboard, and that has cleared the issue. So the next thing that we're going to need to do is find a replacement capacitor and solder that on the board. Now, the best course of action for finding a replacement part is to track down a schematic for the device you're repairing. I have one here for this motherboard, which is an LAH501P. So try and track down a schematic. That is your best friend for doing this. If you absolutely cannot find a schematic, then you can try looking at nearby components that are matching in the size of what you've removed. If two capacitors are the same size and look identical, there's a good chance they are. However, in an ideal world, you should always check the schematics. So let's have a look through here. The particular capacitor we removed was not labeled. However, it was connected to PU1801. So let's do a search for that. PU1801. And it looks like that is our 1.8 volt regulator for something on the GPU. And if we have a look at where it gets its power, it has a connection to the 19 volt main power rail through PJ1802, which will be the jumper that we just resoldered. So we've got a bunch of capacitors listed here. It's going to be one of these guys. And I didn't see any of these guys on the board, but we can take a pretty good guess. The capacitor we removed was an 0603. So that means it's going to be this guy or this guy. and they're both 10 microfarad. U is the symbol for micro, so that is 10 microfarad. So it doesn't matter which one of these it is, they're both identical. So we just need to drop in a 10 microfarad capacitor and we're done. Now, I've only got 0805 capacitors on hand, but that's fine. You can usually fit an 0805 capacitor onto an 0603 pad. So we'll just pop this guy in. He's a little bit on the large side, but that's okay. He still works just fine. This is what happens when you try to be a soldering iron hero when you're making a tutorial video, everyone. I should have just tried to hot air this. There we go. That's on. We'll make sure that has a proper connection in a moment. I'm just going to redo that jumper one more time. There we go. And let's just spray some alcohol on to tidy that all up. There we go. And let's just double check that we have the correct connections to that guy. So we should have a ground connection on that side, which we do. And we should have a connection to the main power rail on this side, which we do. And we should not be shorted to ground, which we're not. There we go. Okay, I'm now going to get this thing reassembled and we should have ourselves a working laptop. I'll see you guys after the cut. Right, we've got enough of this plugged in to give it a test, so I'm going to carefully open it, being careful not to rip the hinges while the bottom case is still off. Plug in the power cable. And we've got, I can't fit it under the camera now. Ooh. We have a light on the charger, which is always a good sign. And if we press the power button, we have fan spin, a power light, and keyboard backlight, and RAM training. It's normal for a laptop to take a while to post after you've messed around with it like this. Sometimes it might power cycle a couple of times. Yeah, this one just turned off. And it's turning back on again. I'll let this run in real time just because, again, sometimes it's important to see. It's easy in videos to just jump cut through dead spots to get the video runtime down. However, sometimes it's important to say, no, look, sometimes they do actually take a while to come up. It just power cycled again. Probably going to go this time. I normally expect 3. Yeah, I just saw a flash. There we go. There we go. Beautiful. That's it. That is how you fix a gaming laptop with voltage injection properly and safely. So I hope you guys found that helpful. That is the proper way to do it. And if there's any pros in the chat who want to share additional hints and tips and stuff that they've seen people do that they really shouldn't, leave a respectful comment below for people to learn from. Because again, this video is about getting the correct information out there and showing and trying to deliver that information that other people don't talk about. I skip over it more often than not in my videos because you're looking for that win. You're looking for the win, not always just to remind everyone of these boring extra steps and boring extra checks and the don't do this, don't do that. It's important. Too many people blow up stuff that otherwise would have been fixable. Right, thank you everyone for tuning in. Thank you to all of my Patreons, YouTube members, and Twitch subscribers, and also to all the viewers, of course. I'll see you guys in the next one. Bye for now.